I gave my seminar last year, but it is great to come back in person and get the actual Stanford experience. I think the Stanford experience started this morning in my Uber to the university. I had talks about consciousness with the Uber driver, so I was really getting the full experience there. So the plan for today is to tell you give you a little bit of an update about the progress we made on spatial perception for robotics pretty much since my last seminar. And I will start with a slide just giving plenty of credits to the students, postdocs, and collaborators doing the hard work and the heavy lifting behind the slides I'm going to present today. So for those of you who don't know my lab, I'm the director of the Spark lab at MIT, and we focus on spatial perception and vision-based navigation. We have a particular emphasis on motivating applications which are safety critical, high integrity, and highly interactive. So example of safety critical applications are search and rescue and maybe self-driving. Here, if the vision-based system is failing, maybe you can fail to find survivors, or maybe you can crash your self-driving cars. We care about applications which are high integrity. For example, the rocket here on the right-hand side, maybe there is no human on board, so it's not safety critical, but it's still a pretty expensive piece of equipment. You don't want to break it. And we care about applications that we call highly interactive. Here, we are interested in all sorts of interactions. Interaction within multiple robots, interaction of the robot with the environment, or interaction between robots and humans. So for today, before getting into our technical contributions, I want to start kind of with a video which is highlighting the type of capabilities that we want to develop for our robots. It's not a real video, it's like computer animation, but it's a good summary of the capabilities we want to develop. So in the video, what you see is a drone which is able to do very aggressive and natural, navigation in complex environments. So the robots are doing, in this case, some vision-based navigation. They're able to understand objects and agents around them. They're able to do this clever interaction with objects. And they're even able to do interaction among each other. Okay, so large swarm of robots interacting in a very natural way among each other. So for today, I want to tell a little bit of the work which we are doing towards this kind of vision of robots with this kind of navigation capabilities. And I'm going to touch on three main foundational topics we've been working on, which hopefully are bringing us closer to this vision of these capable drones. Okay? So today I want to talk about robust estimation as a first topic. I want to talk about hierarchical representations, and then I want to talk about self-supervised learning. And I'm going to use this slide a little bit as an outline of the rest of the presentation. So for the first two parts, robust estimation and hierarchical representations, I will focus a little bit more on localization and mapping problems, or SLAM problems. For the last part, I will talk about object understanding instead, so self-supervised object pose estimation. So let me start with the robust estimation part. And the point I want to make in this part of the talk is that new and old tools from robust estimation enable unprecedented robustness in localization and mapping problems and unlock performance guarantees. I told you about some of the tools, last time I gave the seminar in 2022. I will try to cover a different set of algorithms and to give a little bit of a summary of the progress we made on these topics over the last several years. We've been working on this for more than 6 years now. But let me start by telling you why we care about robust estimation. Robustness to what, exactly? So the context is that we care about robustness in the context of localization and mapping problem. And in localization and mapping problem, typically the first thing that you do, or a key element of simultaneous localization and mapping systems, is to reconstruct the trajectory of your robot. Let's imagine we deploy the robot in a completely unknown environment. The first thing that we want to do is that the robot is moving over time 1 and time 2 is covering a trajectory, and want to reconstruct how the trajectory looks like. Okay, I want to solve an estimation problem to reconstruct the trajectory. What we are given in terms of measurements are relative measurements within different poses in the trajectory. For example, we can measure odometry, which is telling how the robot moved from time 1 to time 2 to time 3, and so on. And we typically in SLAM also have what are called loop closures, which are measurements of poses which are far away. For example, these dashed lines will be loop closures. The way you get these is typically through place recognition methods. There is a computer vision system that is telling you, look, pose 1 and pose 7 are observing the same piece of environment, the same part of the environment, so you can figure out what is the relative relation between these poses. And from all this set of relations, which you can think as being associated to the edges in this graph, you want to reconstruct poses associated to the nodes of this graph. Now, the challenge here is that many of these measurements will be reasonable, will be like, noisy, but still fairly accurate. The odometry is going to be noisy and prone to drift, but will be relatively accurate. The issue is that for modern systems that use for place recognition, you will have a bunch of outliers. You will have a bunch of measurements which are complete garbage. And it's pretty intuitive why that is the case. You might have two different poses which are observing an environment that looks kind of similar, but they are two different environments. They just look similar, but they are different portions of the environment. This is something that is typically called perceptual aliasing in robotics. So essentially, some of the measurements, some of the loop closures are reasonable, some of the others are completely, wrong measurements, are complete outliers. Why do we worry so much about these outliers? Well, let me show you an animation here. So imagine that here I'm solving some problem in which I want to reconstruct the trajectory of the robot, which is this blue line. If I have 0 outliers, I get a reasonable reconstruction of the trajectory. If I have 5 outliers over thousands of measurements, the trajectory reconstruction is very deformed already. If I have 20 outliers, which is a tiny portion, tiny percentage of measurements, the entire trajectory is complete garbage, right? We are not going to do any navigation or any mapping for this type of, using this type of trajectory. So we studied how to get robustness to outliers. And of course, you can go back a few years, several years actually, to the 60s, and people will tell you from robust statistics that to get robustness to outliers, you have to use some robust cost. Okay? So imagine that you have an optimization problem in which you want to figure out the trajectory x of the robot, given a bunch of measurements y. Robust statistics will tell you that what you have to minimize is the robust loss function, which will get you some robustness to these bad measurements. The issue is that people from robust statistics didn't tell us how to optimize, actually, this cost function. And it's provable. We proved that there were results proving that it's intractable to try to solve this optimization problem to optimality. And we also proved that it's even hard computing an approximate solution to this optimization problem. So we spent a number of years trying to understand how to solve better these optimization problems and how to get performance guarantees. So one of the algorithms we propose is what is called graduated non-convexity. The realization is that the hardness of the optimization problem is due to non-convexity. And the insight behind graduated non-convexity, let me play this again, is that instead of solving directly the original optimization problem, maybe we can start from a convex approximation of the problem. And iteration after iteration, we can increase a bit more the amount of non-convexity until we recover the original non-convex cost. And at each iteration, we use the solution from the previous iteration as initial guess from the optimization, with the result that our set of solutions will track this wide path and eventually get to the optimal solution. So this algorithm, extremely robust to outliers for this SLAM problem. We get robustness empirically to 70, 90% of outliers that you find in practice, which is much, much better than having robustness to 20 outliers, as in this case. So the type of performance that you get in real problems is that you try to figure out the trajectory. There are a bunch of outliers, which are these red lines. Graduated non-convexity is able to solve this optimization problem and figure out which are the outliers, and will result in a much nicer map reconstruction. If you paid attention to my slide about the message of this part, I said new and old tools from robust estimation are going to be useful to solve localization and mapping problems. And indeed, for those of you who are really, maybe senior faculty members working in computer vision, you realize that graduated non-convexity is not a new algorithm. It's something that was proposed in the 90s to solve a very different problem, depth reconstruction in images. What we did here is to rediscover it and apply that to a completely different setup, which is pose estimation in the context of SLAM. So, I want to show the impact of this kind of algorithms across a number of applications. We've been using graduated non-convexity for a number of problems. In this case, I'm showcasing it for an application of underground mapping in the context of the DARPA Subterranean Challenge. So we did this fun challenge with JPL and Caltech, where the goal was to deploy robots in very challenging underground environments and having them map the environments with very high accuracy. And through the use of graduated non-convexity in our SLAM system, we are able to pretty much get pose estimation errors, like localize the robot with sub-meter precision over very long trajectories. And again, this is a case in which is, of course, GPS denied, is underground, but also the robot has no idea about the environment. So it's completely unknown environment. Part of this allowed us to get competitive results in the DARPA challenge. We were second and first place in 2 out of the 3 competitions. The last competition didn't go as well, but that's another story. We'll do that over beers maybe. And all the code, you will see that as a pattern, I guess. We tend to release as much open source code as we can. So if you want to try out some of these contributions, you will find them on GitHub. With Ford, we applied these ideas in the context of self-driving and in particular mapping for autonomous valet parking. So in this case, you have, imagine you have a car with 4 cameras around the car. You're trying to map, for example, a parking lot. So what you see here is that the car is driving around, and we are doing mapping of the parking lot. You will see maybe some of the parking spaces here, but you're able to do this just with a bunch of monocular cameras and very cheap cameras as well. Slightly more challenging than the setup I show for the subterranean challenge, just because now we have monocular cameras. And essentially, the loop closures are going to be measured up to scale. So there is some ambiguity in the reconstruction, but you can still do an excellent job and reject outliers through graduated non-convexity. And just to tell you, how much accuracy you can get through these algorithms, in the table I'm showing, again, the errors in meters compared to the length of the trajectory for many data sets, comparing the proposed approach with the 2 state-of-the-art SLAM systems, Vince Fusion and OrbSLAM 3. And you can see also that we express the drift, which is the error as a percentage of the trajectory traveled. So these SLAM systems, first of all, can give you very accurate trajectories in which the drift is a tiny fraction of the trajectory traveled. But also, with these cool ideas from robust estimation, you can get just much better accuracy over very competitive great systems such as Vince Fusion and OrbSLAM 3. So from self-driving to space, we have been using some of these ideas from robust estimation also for terrain relative navigation, which is the problem of estimating the pose of a rocket in this case during the descent phase. I will not mention too much about this. This is a cool collaboration we did with Draper. But the cool thing about this is that we're able to run some of our algorithms on these 2 platforms. So a high-altitude balloon and the Blue Origin New Shepard rocket. So my students were pretty excited to put algorithms on the payloads of these rockets. Very challenging problem, this platform navigating at very high altitude, very large speeds with clouds and so on, so very challenging conditions. And you can get to a decent localization error through robust estimation and so on, which of course is not going to be sub-meters, but is going to still be compatible with for example, entry phase or terrain relative navigation in this case. Okay, so I want to maybe conclude this part just by summarizing. I told you about this graduated non-convexity idea, but the truth is that my group has been working on this topic of robust estimation for perception for a number of years. I want to do a 1-slide summary of the other contributions we did, just in case you are interested in this area, if you want to read more. So the idea is how to solve this kind of robust estimation problems. I was showcasing applications to localization and mapping, but the truth is that this kind of problems show up in pose estimation for objects, using point clouds, images for SLAM, and so on. So it's a very general tool. And what we did in our research is to develop literally a toolbox of algorithms, not a single algorithm, but a set of algorithms to solve these robust estimation problems more reliably and possibly with performance guarantees. So I told you about graduated non-convexity. The algorithm actually works so well that it's now included in MATLAB, if you're curious about that, in the navigation toolbox in MATLAB. We have graph theoretic approaches which are able to prune outliers by reasoning over compatibility between measurements. And I think last time I was giving the seminar, I was telling more about moment relaxations, which I think is one of the coolest things that we have done, in which the idea is to use semi-definite, convex semi-definite relaxations to get provably optimal solutions for this optimization problem, which is something that nobody was able to do before in robotics. So there is some recent progress on that, like also including this idea of estimation contracts. I will not cover that too much today, but I want to stress that part of our work is about designing certifiable algorithms which carry some performance guarantees, in the sense that our algorithms either compute an estimate that can certify the optimal estimate, or they can detect failure otherwise. Okay. So after this summary, I'll switch gear and actually talk a little bit more about hierarchical representations instead. And the point I want to make in this part of the presentation is that highly interactive robotics applications require metric-semantic hierarchical map representations and real-time 3D scene understanding algorithms to build them. So what do I mean by interactive applications? Imagine that I have interaction with humans. I would like for my robot to understand and execute very complex instructions. For example, I want to tell my robot, go grab me the cup of coffee on the table in the kitchen. What I'm arguing is that in order for the robot to understand and execute these instructions, we'll need metric semantic and hierarchical map representations. I don't think we'll need too much convincing to do in convincing that we need metric semantic maps. Of course, if the instruction is robot, go grab me the cup of coffee on the desk, the robot will need to know about geometry, right? We'll need to know how to get to the desk, how to avoid obstacles along the way. But we'll also need to know about semantics, which is what is the cup of coffee, what is the desk, and how to detect them in the scene. So a few years ago, we developed a library for metric semantic mapping, which is called Chimera. The high-level picture of what Chimera does is Chimera is taking a bunch of camera images as well as inertial data, is applying segmentation, semantic segmentation to the image, and then is mapping this 2D understanding of the environment into a 3D map. So you can imagine that the robot is going around and is building a 3D mesh of the environment in real time. This is a very lightweight algorithm, so everything is running on CPU. But not only can build a 3D map of the environment, the map also has different colors which correspond to different semantic labels, right? So green maybe are the chairs, blue are the desks, yellow are the cubicles. So this is an example of metric semantic map in which the robot finally can understand the identity and the semantics of different objects in 3D. We have a bunch of extensions. We work a lot on these topics. We also have extension to multi-robot systems. But after working on these, we quickly realized that metric semantic mapping is actually not enough for the type of interactions we're envisioning with our robots. That's fairly easy to explain. Imagine that I want to tell the robot, go search for survivors near the fridge in the kitchen. We realized that in order for the robot to understand this instruction, the robot will need to understand semantics beyond objects. For example, you need to understand rooms in the environments. The instruction involves the notion of kitchen, but if you are just mapping flat objects in the environment, the robot will have no idea about what the kitchen is or where the kitchen is. And second, this kind of instruction requires reasoning over relations within elements in the environment. For example, the instruction says that the fridge is in the kitchen. So we have to understand what that relation means. Okay, we need a map representation which is encoding that relation. So over the past year, we've been working a lot on this new representation, which is called 3D scene graphs, in which you start modeling semantics at different levels of abstraction, and you start thinking about relation between objects. What a scene graph is just a hierarchical map representation in which at the bottom layer, you have a 3D metric semantic mesh, pretty much the same that I had in previous slides. But as you go up in the hierarchy, you are abstracting away the mesh into objects, places, rooms, and buildings. I guess rooms, buildings are fairly intuitive. Places are just a representation, topological representation of the free space. So you can imagine that as a graph of free space that represents traversability between different places in the environment. So actually, we're among the first to propose this representation. I think the first work proposing this representation is from Iror Meni, who is a faculty here in civil engineering, so very cool work. What is ended up doing over the last year is to be a little bit more rigorous about why a hierarchical representation is needed. And in this slide, I'm comparing essentially a flat representation in which you just have voxels and maybe you're attaching a bunch of semantic labels to voxels against the type of hierarchical map representations we are proposing. And we realized that, first of all, hierarchical representations scale better. It's like a trivial point, I would say, if you have to store a bunch of attributes to each voxel. The scalability of this map will increase with the number of semantic labels and with the number of voxels. If instead you arrange things as a tree, you can essentially group concepts together, and the scalability in terms of storage and memory will get much, much better over time, which is great. Simple, simple observation. The second observation is that if you care about modeling relations, modeling relation is pretty easy. If you have a graph-based representation, you can just capture relations as edges in the graph. For example, you can model that the stove is close to the fridge, or maybe the kitchen is connected to the dining room. But something that we proved, which is a little bit more fundamental, is that this type of what we call hierarchical graphs have low tree width. So the tree width is a fundamental property of a graph. And proving that a graph has low tree width is pretty much allowing to conclude that it's fast to do inference over this graph. Okay, so it's much nicer to have graphs with low tree width. And in a few slides, this notion of tree width will allow us to get some approximation result that you're going to see applied to even graph neural networks. Okay, so not only we prove that this representation is much nicer in terms of scalability, tree width, and so on, but we also designed the first algorithms to build this type of 3D scene graph representation in real time using sensor data. Hydra is a name of the system which is putting these things together and is allowing 3D scene graph construction. So imagine that our robot is starting in a kitchen without prior knowledge about the environment. What these systems are doing is to allow the robot to estimate its own trajectory, pretty much like the same trajectory estimation problem I was covering before. Is allowing the robot to understand objects and the semantics of objects nearby, sink, fridge, and so on. And then from these semantics of objects, drawing conclusion about what are the different rooms in the environment, kitchen, bedroom, and so on. So I will not tell you too many details about these, but you can imagine that these actually, to me, is kind of the evolution of the traditional SLAM problem. Okay? There is some SLAM problem in solving for the mesh reconstruction at the bottom layer. So there is some metric-semantic reconstruction. But then to get to this 3D scene graph, you have to do much more. First of all, you have to do more geometric reasoning. For example, you have to extract the free space, which is this layer of places in the scene graph. And you do that by doing what is called a generalized Voronoi diagram. The second thing that you have to do is to cluster the places into different rooms. And here we use tools actually from topology. There is a tool which is called persistent homology, which, given a graph of places in our case, we break down the graph into different rooms. And then to reason over the semantic of the different rooms, you're going to see in a while that we use tools from geometric deep learning, and in particular graph neural networks. I will cover that in detail, a little bit more details in a couple of slides. The exciting thing about this work is that this is not just really a robotics work. Right? We can run, and we paid attention to being able to run these algorithms on real robots right now. So we're doing all sorts of demonstration with these. I'm going to show you, just a quick demo with a robot mapping, a building at MIT. But the bottom line is that we can run these on onboard computers, for example, the Xavier NX, and constructing the different layers of a scene graph in a matter of milliseconds. We can do all these in real time on a real robot. So last time I was telling you a little bit more details about maybe how to form the lower layers of this representation. For today, I want to cover a single topic, which is how to attach semantic labels to the top layers. So let's say that I'm building a scene graph as the robot moves through the environment. I'm able to cluster the environment into different rooms. In this case, R1 to R16, I guess. How do I attach labels to this room? How do I know if a room is a kitchen versus a bedroom? So I would like to tackle that problem and tell you a little bit the tools that we develop to tackle that problem. First of all, I want to tackle the elephant in the room here. Just checking, maybe this is an easy problem. Maybe the progress we made in vision language models, kind of maybe it's easy to classify and to understand the environment and the different rooms in the environment. It's easy. Maybe I just have to take a snapshot of my reconstruction and I have to pass it to a vision language model and query what are the rooms in the environment. Maybe it's that easy. So I tried that. I took the interface for Lava. I uploaded one of the 3D reconstructions we have, this is a point cloud. I can ask Lava to describe the point cloud. kind of makes sense. I will not read this into too many details. Then I start having a little bit more targeted questions. The question asked is, how many bedrooms do you see in the image? Right? We're interested in room classification. How many bedrooms do you see? And the language model is replying, there is one bedroom visible in the image, located in the open concept living space. Well, you stare at the image, you say, okay, I count at least 1, 2, maybe 3 beds and bedrooms. So this doesn't sound quite right, but maybe the language model is just not paying enough attention maybe to the image. So let me try to help a little bit. I say I can count 3 beds. Okay, and the language model reply, I apologize for the confusion. Upon further examination, there are indeed 3 beds. So then I ask again, so how many bedrooms do you see? Says, okay, finally there are 3 bedrooms. So maybe just didn't pay enough attention in the previous stage. But then I keep going and I say, upon further inspection, I can count 2 beds. And then it starts agreeing with me that there are 2 beds instead. So I can steer essentially the language model to tell me whatever I want here. It doesn't seem that there is enough really understanding of the image. But then I say, maybe I'm trying with the problem which is too hard. Maybe the reconstruction is noisy, is incomplete. Maybe I have to pass a top view of the environment and maybe I make it into a floor plan with room labels. I mean, that should be easy. We start a new conversation. How many bedrooms do you see in this picture? 1, 2, 3, and 4. And then it says that there are 2 instead. So yeah, I think you can prompt your way to getting the exact answer, but that is not the point. What I'm arguing is that it's not as easy. The language model will not have an immediate understanding. Even in a very simple problem, will not have an immediate understanding of rooms in the environment. So therefore, we have to come up with tools which are a little bit more clever. And today I'm going to tell you, in a couple of slides, maybe the tools that we developed. Again, the problem is that you have this scene graph, and you want to come up with semantic labels for the different rooms. Semantic labels being kitchen, bedroom, and so on. And we do this as humans all the time. The way I think we do that as humans is that we look at the objects around us. And from the objects, we can really easily understand what is the room type we are traversing. So for example, if in a room there is a bed, there is a chair, there is a book, maybe we can conclude that that's a bedroom, right? So we would like to do the same type of inference with our robots. The old style version of doing this type of inference would be something like a probabilistic graphical model. For that, we need to hard code a lot of information. The modern version of that is to use a graph neural network. How many of you are familiar with graph neural networks here? Maybe half. So in a graph neural network, you have a graph with nodes. Imagine that 5 is the room node, and these other 4 are objects nodes. What you do is you do some message passing to form embeddings at each node, and then you classify these embeddings into, bedroom, bathroom, and so on. So it's just neural message passing over a graph. We use this indeed as a baseline, but we actually propose something that is a little bit more clever. It's a new graph neural network, which is something that we call the neural tree. And I'm going to present this idea in a single picture just because it's really that simple. I can present this idea in a single figure. So the idea of the neural tree is that you do not have, what we say is that we do not have to do message passing over the original graph. What you have to do is to transform the graph into a tree using something that is called a tree decomposition. And then you have to do message passing on the tree instead. And if you do this trick, you just gain performance guarantees, and you get much better performance in practice. Okay? So for the few of you who might be very familiar with probabilistic graphical models, you might have seen the junction tree algorithm. What we are doing is essentially a neural version of a junction tree algorithm. So we are bridging insights from graphical models and graph neural networks together to get performance guarantees. So what do we gain by doing this neural tree architecture? First of all, we gain theoretical guarantees. There is a long statement, as a theorem. I will just summarize what are the main points. Imagine that F is a probability distribution over the graph that you care about. And let's call G the set of functions that can be implemented to your graph neural network, to your neural tree architecture. What we prove is that you can find a G which is close enough to any probability distribution up to an error epsilon. And you can do this using a number of parameters, which you can imagine as the weights in your neural network, which is this capital N. And the number of parameters grows linearly in the size of the graph, which is good, linearly is good, and only grows exponentially in the tree width of the graph. okay? But we just proved that scene graphs has small tree width, right? So essentially what I'm saying is that with this result about the tree width, we can prove that these architectures are probably expressive over scene graphs with a small number of parameters, okay? So in a nutshell, again, let me repeat this. The neural tree will need a parameter which is exponential in the tree width, but the tree width will be small for scene graphs. Okay, so maybe we don't care about the theory, we want to see how this works in practice. So we do experiments, in this case on the Stanford 3D scene graph dataset, in which there are these pairs of objects and rooms, and we evaluate the percentage of things which we classify correctly. Of course, we would like for this to be 100%. Like, you know, these percentages are what we show in the table, higher the better. And in the table, we compare different types of message passing, graph attention, like, you know, and other types of message passing. We compare doing message passing on the original graph, which is standard graph neural networks, against the neural tree architecture, which is what we propose. And you can see that just by doing this trick of the tree decomposition, we boost the performance by 10% in many cases, substantial boost in performance with really a minor addition in the pipeline. And by the way, because our graphs have small tree width, it means that the tree decomposition is not huge, which means that the runtime of these algorithms of traditional graph neural networks and neural tree are not very different. So we don't lose much in terms of computation. Okay, so I want to stress now for a couple of slides just some very recent extension of this 3D scene graph work. This is something that will be on archive hopefully today. It's something that we are pretty much finalizing right now, which is the observation that hierarchical representations are not just for indoor environments, but it makes sense to define hierarchical representations in arbitrary environments. Okay? So imagine now we have an outdoor environment. We can still reason over the mesh of the environment. We can reason over objects, places which represent traversability. But then instead of classifying things into rooms, buildings, and so on, we can classify them into maybe field, road, park, and so on. There is still a hierarchy that we can leverage in outdoors. So the question we ask is, can we adapt our algorithms to reason over arbitrary, possibly outdoor environments? And the way we're thinking about this problem is a problem of classifying places into high-level regions. So I want to take this graph of nodes, which are the black nodes, and I want to classify if a place is part of a field, is part of a road, and so on, leveraging possibly semantic information from the lower layers, which is, for example, which objects are nearby for each place. So in theory, I could solve this with the neural tree. I can solve this with a graph neural network. But there are two challenges in outdoor environments. The first challenge is that I'm not really sure which concepts to include in the scene graph, right? I do not have rooms. Like, I can have very arbitrary set of concepts. And I really don't want to do the job that for every testing scenario I have to come up with a different set of objects. I would like to automate that process. The more fundamental problem is that there is a lack of training data. For indoor scene graphs, there are a bunch of training data sets. For outdoor, you can think maybe there is Google Maps and things like that, but actually there are no data sets which are connecting these high-level concepts with the objects in the data set. Okay? It's not easy to do training at all. So we try to solve this problem with a couple of contributions. The first one is to create a spatial ontology. An ontology is just a graph of concepts and relations. So the idea is that we have to define an ontology which is summarizing the set of concepts we care about, dividing concepts between high-level concepts, like, this can be the equivalent of rooms, but can be fields and things that apply to outdoors, and low-level concepts, which are pretty much the objects. And we can also establish relations which are saying, for example, a bed is more likely to be in a bedroom, a kitchen is very likely to contain a fridge. The twist that we have, of course, ontology, have a very long history. The twist that we have is that we let a language model actually populate a very dense ontology for us. The main problem in building ontology is that once you scale the number of concepts and the number of ages, it's very tough for a human to populate that. We just query a language model with things like which key elements from the lowest layer are most distinctive about a higher level concept. For example, what are the objects which are more distinctive of a kitchen. Okay? And with the response of a language model, we populate all the edges in the ontology. The other thing that I think is pretty cool is to use to try to use the structure of the ontology to help learning, in particular in a case in which you do not have a lot of training data. And to do that, we use a tool which is called logic tensor networks. Logic tensor network, in a nutshell, are tools to enforce logical rules as part of the training of a neural network. So for example, in a neural network, I want to give my neural network a bunch of training examples, but then I want to make sure that the prediction of my neural network are consistent with the ontology. I want to make sure that the neural network is not predicting that the rock can be in the bedroom. Okay? So I want to enforce these as kind of hard logical constraints on top of my training data. Logic tensor networks will allow just that. And just to give you a very brief summary of what's going on, logic tensor networks will use a loss function, which is not the typical cross entropy and so on, but will be a cross function which is quantifying satisfaction of a set of formulas, logical formulas. These are the phi. And of course, if you think about logical formulas, typically you think about kind of 0-1 satisfaction. What logic tensor network does is to use real logic in which you relax satisfaction in the interval 0-1, and you make everything differentiable just by just relaxing satisfaction in 0-1. Okay? So it's a differentiable logic. That's one way you can take this. The advantage of this is that now we can use partially some training data for during training of our graph neural network, but we can also use the spatial ontology to kind of support, to provide a supervision signal for the neural network itself. Okay, so let me show a couple of slides with results here. Qualitative results are on the right. In this case, I'm starting with indoor environments just because we have a lot of data for testing in this case. So you see here the environment being split in different rooms and all the room labels. And here I have the quantitative results. So the quantitative results are showing the accuracy of the classification of the rooms in this case for decreasing amount of training data. Okay? So here I have close to 100%. I have lots of data. Here I have very little training data. What happens is that if you have lots of training data, if you use, for example, here cross entropy, you have very good performance. And the proposed approach, which is based on this logic tensor network, will have pretty much similar performance. So when you have plenty of data, you probably don't need this logic tensor network. But as the amount of training data drops, essentially the cross entropy, standard cross entropy formulation will just drop, and we'll get to essentially random guessing of the labels. And instead, the proposed approach will approach a lower bound, which is the amount of information in the spatial ontology. Okay? So in other words, if you remove completely the training data, the proposed approach will still know correlation between objects and places through the spatial ontology, which will guarantee a minimum level of performance. Okay? So if you're here, you probably don't care about logic tensor networks. If you have very little data, they can make a huge difference for you. So for different projects, we try this out in outdoor environments. The results are quite easy to understand already from the figures. What you see in the figures are ground truth labels, which are the polygons here. And the color of the classification is the result of our network. So essentially, if all these dots a green color with the bounding box, it means that we are classifying correctly. If instead they don't agree, like in this case, for example, the color doesn't agree, it means that the classification is incorrect. And we see that we are able to do a decent classification of many different concepts in large-scale outdoor data sets involving roads, buildings, forests, and so on. This is an experiment with the Army Research Lab at West Point, as well as dealing with completely different environments. This is a beach, seaside environment close to Boston. And I will not spend too much time about that, but it turns out that with these logic tensor networks, you can even predict at test time concepts that you haven't seen at training time. Just because the ontology can encode relations that maybe you haven't seen at test time, we can do even prediction, kind of zero-shot prediction of objects, of regions that you haven't seen at test time. Also, in this case, we really care about running these on real robots. So I'm showing just an experiment of a real robot running in the courtyard near to our building at MIT. The robot, of course, is building this map, semantic map of the scene. Is isolating different objects, for example, chairs versus boxes and so on. And if you see, maybe let me restart this. If you see on top of building these low-level concepts, the logic tensor network will allow to segment the space into different regions. So for example, we'll find that there is a walkway, there is some off-road terrain, and we're going to see this a little bit better in a few seconds. Okay? So that's the type of performance that we get. Again, like, the real image here and the real-time reconstruction on this side. Like, there's a little bit of an acceleration, just to be fair. The robot is not moving that fast. And you see that the logic tensor network is getting from objects to classifying. Should really cut this video in a better way, but let's see if I can. So in this case, these top ones are the places, and they're classified into different semantic regions. And I think it shows a little bit better later in the video, but I think you got the point there. So to close this part, I was insisting a lot on this idea of hierarchical maps for robotics. Now that we have these maps, or we made good progress on these maps, what can we do with them? And in this slide, I'm summarizing that there is a lot actually we can do with them. We have been showing, even in the original paper that we proposed about scene graphs, that you can do now hierarchical path planning. You can speed up motion planning a lot on these maps. You can apply reinforcement learning, and you can do object search with much better performance compared to pixel to action approaches. And you can even use the scene graph to reduce the amount of communication in multi-robot systems. The thing that was reassuring is that the work at the bottom is from actually different groups that also found scene graphs to be very useful, in particular for problems involving task or task and motion planning, as well as goal navigation, and then we show improved performance when using these hierarchical models. And there is a lot more to be done, in terms of human-robot interaction, monitoring, prediction, and so on. But this model seems to be pretty useful for robotics. So I want to spend the last 5 minutes or so here talking about self-supervised learning. I will make this quite fast. The basic observation here is that for safety-critical robotics application, we need algorithms, perception algorithms, that are able to distinguish correct estimates from incorrect ones, and we want them to adapt in a self-supervised fashion. Why do I care about failures and adaptation? Well, even if you take the latest foundation model and so on, there are always going to be errors, in particular in scenarios which are not the typical ones that you encounter in the training data. If you don't believe that, I just took a random image from the web. Of course, it's a robot in kind of a fire scenario. And I passed this to a transformer-based semantic segmentation architecture. One former is a pretty good, reasonable baseline, is a very recent approach. And you see that even this state-of-the-art transformer-based method will classify the robot as a fire hydrant and the fire as a light. So definitely, we have to worry about failures, even if we go for large foundation models. So we started thinking about essentially self-supervision for object understanding, and in particular for object pose estimation. So it's a little bit more geometric than this example. So let me set the stage a little bit. So in the first part of the talk, I discussed a lot about robust estimation, right? I said that robust estimation can be applied to localization and mapping problem. In this part of the talk, I'm going to apply that to a pose estimation problem for objects, in which I say that I pass to the robust estimation a bunch of measurements of points on the object I care about, and I want the robust estimator to figure out what is the pose of the object I care about. What is the role of learning in all that? The role of learning is that typically these measurements, these detections of the object are produced by a neural network, right? So what I ask is that now that we have much better robust estimation techniques, can I use them to self-supervise the neural network? Okay? So can we self-supervise a neural network using certifiable estimation algorithms? What I'm going to argue is actually that certification and self-supervision are very coupled topics. If you solve one, you're very likely to be able to solve the other as well. And I will show you the insight, I will keep it high level, but I will show you the intuition behind that just with a simple animation. So imagine that you have a pre-trained neural network, okay? A neural network which is trained maybe just in simulation. This can be maybe a foundation model, a pre-trained model. And imagine now that I'm going to expose that to real data which is unlabeled, okay? So imagine at test time, I provide a batch of 3 samples to my pre-trained neural network. So what happens is that I can just do a forward pass of the neural network. The neural network will predict a bunch of key points, and then I can do my robust estimation algorithms to predict the pose of the object. Now, if you have a certifiable algorithm, which is an algorithm that is able to distinguish correct estimates from incorrect ones, I'm able to understand which of the results is correct and which of the results is wrong. And I can do something very simple. I can take the correct one as a pseudo label and backpropagate the result to improve my neural network a little bit. And then I can try with another batch of data. The network now improved a little bit, and maybe in this case I produce 2 correct results, and I can backpropagate this a bit. And then I can keep going, incrementally improving the quality of my neural network, again, without any labels. Essentially, the pipeline, by certifying which outputs are correct, will create labels on the fly, okay? Pseudo labels on the fly. Okay, so we applied this idea for object pose estimation. We are giving RGBD data. We have to estimate the pose of an object in the image. Again, there is a neural network that we want to kind of self-supervise and improve over time. We have this robust corrector, which is our robust estimation module. And we have certificates which are in charge of deciding if we got the right estimate or the wrong one. And the type of performance we get is summarized by this video. So we start at the initial iteration in which the pre-trained network is not doing great. So you see that the prediction of the object doesn't match the point cloud very well. But the more self-supervised iterations we do, the better, the point cloud in green is aligning to the object, which means the better job we are doing at estimating the pose of the object. And all of these is just improving the performance of the network without the need for any supervision from a human. So we pushed this is a more recent line of work. We pushed this in a couple of papers. At RSS, we actually shown that we can apply this idea also if you put multiple models in parallel. So if you have an ensemble of models, you can kind of self-supervise them at the same time, and you can take advantage that maybe one model is cross-supervising the other, and so on. So you can apply this idea to an ensemble of models instead. I will spend maybe one slide about results, and then I know we'll have to stop. But you can look at the performance of maybe this video, this figure. This is the cumulative distribution of the errors. You want this to be on the left as much as possible. The proposed approach is in blue. We actually do pretty well compared to a fully supervised baseline, and we do much, much better than self-60++, which is a self-supervised baseline. We have been applying this idea for all sorts of problems. NASA is using this for lunar tower assembly. We're doing a project right now for warehouse automation in which we do pose estimation with these methods. And we're having fun also using these kind of pose estimation methods for aggressive aerial manipulation, as you can see in the video on the right. Maybe let me get to the real demo. So we can do aggressive manipulation of objects just by detecting them in real time. So in summary, today, hopefully I cover a lot of ground. I hope you saw some of the progress we made on robust estimation, scene graph and hierarchical representation, and self-supervised learning. And hopefully that will bring us closer to having agents that can interact with objects and with the environment and do vision-based navigation. So I wrap up here, thanking the sponsors and, of course, thanking you for your attention. Right.